In this video tutorial, we will look at some acoustic data analysis methods, things to do with your acoustic files once you have obtained and merged them. And these are just ideas for you. There's many methods, many bits of software that you might use, but here are some starting ideas. We will look in this tutorial at three particular tasks and show you how to execute them. For the first task here, which is to measure sound intensity, we'll look at some brief files obtained during a doc test with Minesto and the University of Bangor. Here you see 4 SonarPoint recorders, and they are all cabled to a tetrahedral hydrophone array that's here. You will have seen that in a previous video tutorial. Now let's look at some of the files that we obtained during this doc test. They are already converted to WAV files here, and I also have merged versions of it that I'll use later. And I will select one of them. Let's take this one here, 2130 for recorder 1012. And I'm now opening this with the Audacity software. And again, Audacity is installed by Desert Star on the computer that's shipped with your system. It is a free software, so you can obtain it online. So what we see now here is a time domain plot of this particular recording file. It's a 15-minute recording file. You can see it's just a little bit less than 15 minutes long. There's always that gap at the end of each file, in between each recording file. This is used to reinitialize the recorder. So be aware of that, by the way, this gap as you are defining your recording segment length. If you had 1-minute recording segments, then this period in between them, which is of fixed length, would become a substantial percentage. I'll start playing it just before apparently a boat engine kicks in. Let's listen to that. And here you hear the boat engine starting up. You can jump to anywhere else you want. Or maybe a quiet period. And so on. What I want to do now next, I'll stop playing here, and I want to home in on some significant noise event, or maybe for you would be a signal event, to measure it. I'll swipe over it, left click and go over it. And then I can go view, zoom to selection. And here it is zoomed in some. I can do that again. View, zoom to selection. Notice it's also Control E if you're looking for a shortcut. The final zoom, I'll use my Control E. And here we go. Now, how strong is this sound? This is our first task here. And we can see, well, it's not quite half of full scale. Well, usually we want to have things in decibels. So notice how I did that. Now I'm in the decibel setting. And we can see that the peak of the sound signal is at about -9 decibels, respective the full scale value of this recording. But the question is, what's the full scale value, and how does that relate to absolute sound units, that is decibels, respective 1 micropascal? And in order to really figure that out, we first have to equalize our recording. So we select the section that we want to equalize, and oftentimes you can just make it the whole file. It's a fairly fast process in Audacity. Then I go to Effects, Equalization. Here I now need to call up the curve that I want to use. Here I already have a curve for the hydrophone that we used in this test, the HTI 99 UHF. But how did it get there? I'll show you that briefly. Save Manage Curves. I'll actually delete this one here for now, so we can show you the process again. I'm going to import curves, and these curves are provided by Desert Star for all the hydrophones that we have. I should say each curve is just generic for the hydrophone type, not the sensitivity of the particular hydrophone in your system, or hydrophones in your system. Those calibration curves, we do have them available, the individual ones, not the calibration curves, but the calibration reports from the manufacturer, HTI. The Desert Star in-house ones, the MH or SH hydrophones, which are integrated in the end cap, we don't have individual curves for them. So for high precision measurements, you would want to select an HTI recorder, and please also review the video about hydrophone selection. So I will select this one again to add it to my list of equalization curves. I then select it. Okay, and here's the equalization curve for it that will be used. Here's one thing to really watch out for. Each equalization curve specifies the full scale value, in this case 172 decibels respective 1 micropascal full scale, and this curve is valid between 1 Hertz and 200 kilohertz. So once equalized, the full scale value will be 172 dB respective 1 micropascal. We will do that now. You saw how the waveform got a bit smaller. It was at -9 dB. Now the peak of it reaches about -20 dB. So that's -20 dB, 20 dB below the full scale value of 172 dB. So we are looking here at a peak intensity of this particular sound pulse of 172 minus 20 equals 152 dB respective 1 micropascal. Now that's an instantaneous value. If you want the RMS value, you need to subtract another 3 dB, so 152 minus 3 would be 149 dB RMS respective 1 micropascal. Now let's look at some of the fundamentals of sound source localization, how this is done. Sound source localization is based on identifying the time difference of arrival of the same sound at multiple recorders or multiple hydrophones. To go over that quickly, I already opened up the same file that we used for the sound intensity measurements, but this time the merged version, so we can see that signal as perceived by all 4 hydrophones. And I will zoom in on the same event as we used before. Notice how this event has a very well-defined start, a sudden rise in amplitude, and then there's sort of a tail here. So what I'm going to do is I'm going to measure, I just identify visually the start of the signal as seen by this recorder, and say here by this recorder. Let me zoom in some more. All right. How long is the time difference of arrival between this and this recorder? Here's our scale. Here we are a little past 8 minutes 46.95650 seconds, and then at the end is 0.95660, so that's 100 microseconds later, a little bit less than 100 microseconds is the time difference of arrival. Also, we can tell that this hydrophone was closest to the sound source, so the sound arrived first, and this one was furthest away. Now I want to point out again here that we were using a tetrahedral array with 4 hydrophones, and the spacing between them is 15 centimeters, which is about 100 microsecond signal runtime. So that makes sense. So the sound may have come, for example, if these were the first 2 recorders to perceive it, then maybe it came from over here. You would get some bearing, and including the top hydrophone here, you can also get a vertical bearing in addition to the azimuth or horizontal bearing. How is that processed? There's many ways of doing that. Here, for this particular experiment, the Minesto project with the University of Bangor and St. Andrews University use this software. I actually don't know what it is, but it computes the bearing of click trains from dolphins. We saw that in an earlier video. So here you see a few bearings. So the exact method that they use to obtain their TDOAs is not known to me. Here is, however, a picture of one of these clicks as perceived by the 4 hydrophone, and notice again a very clean start, and then comes the signal, and then we have a bit of a tail. I believe I see some reverberations here. If you look at this here, here, and here, for example. Next, let's take a look how sound source localization might be done with a long baseline array. So an array consisting of multiple independent recorders spaced some distance apart. Here we have one mooring string with the recorder here, and then the next recorder would be some distance away. And in the example that we are using, the distance was about 500 meters. So then you certainly wouldn't see the recorder again, and you might have at least 3 or maybe 4 or some other number of recorders there. In this example, we're going to compare 2 methods of determining TDOA. The leading edge detection is the one we just went through, and the other method is signal cross correlation, and that is arguably the more commonly used method. Signal cross correlation is where you have an algorithm that slides one version of the signal, say this one or this one or this one, against in the time axis against this one, until you get the best match between the 2, and that would be your time difference of arrival. One software that performs signal cross correlation is called Ishmael, and it is a free software. You can see that up here. What you do in Ishmael is you identify your particular sound signature. Here, this is a whale vocalization of some sort. You identify it in your various recorder channels that are available to you, and then the software automatically performs the signal cross correlation and determines the time differences of arrival, which then convert into the sound source location. In the next 2 slides, we will compare how the leading edge method and the signal cross correlation method works as far as providing accurate sound source locations. You have seen this slide before in the video on deployments, and this again is in a reservoir, and we were running a boat, a small boat on a course like this. and towing behind the boat an underwater speaker that was projecting various sounds. And here you see the localization of the sounds using the time difference of arrival method. And you can see they are quite a good match to the boat track. For scale here, this one is 171 meters. Some of these have accuracy called out 1 meter, 3.69 meters, and so on. This slide here now shows overlaid some of the same recordings localized using signal cross correlation in Ishmael, and you can see that it is actually far less accurate. The errors are on the order of several tens of meters here, and the circular boat course is hard to determine. Now, why does the leading edge detection method work so much better than the signal cross correlation method? Well, the reason is that as sound travels through the water, it will find its way to the recorder via a direct path, but almost certainly also via a number of indirect paths. For some more insights on this, let's look at this slide again and notice a click event here, and then what might well be reverberations or echoes following it. Now in this case here, the original direct path event is of a higher amplitude than the reverberation, and you should then get generally a fairly good estimate of TDOA with signal cross correlation. But this kind of scenario is not necessarily the case. Sometimes a reflected signal bouncing off a good surface, like the surface of the water, for example, might be much stronger. And so now you get several correlation peaks, and the most pronounced correlation peak does not necessarily reflect the first received signal, that is the direct signal. It might reflect some other indirect signal that arrived later, thereby giving you a wrong TDOA and thereby a less accurate result. If you compare that to the leading edge detection method, you just look for the first indication of a signal, and that would, whether it's the strongest signal or not, doesn't matter. And this signal then, by definition, will be the most direct signal. So now the question might be, well, why don't you always use TDOA rather than signal cross correlation? And the answer to this, of course, is that the leading edge detection requires just that, a well-defined leading edge. That is generally available for echolocation clicks by marine mammals and, of course, for acoustic pingers. But some of the vocalizations of whales are so gradual that it can be difficult to identify a leading edge or the first instance, the direct instance of some significant characteristic in the sound source, perhaps a significant frequency sweep. Okay, so before I move on, let me give a little call out to BioWaves. Desert Star and BioWaves are cooperating very closely. At Desert Star, we are developing the hardware like the SonarPoint recorder, and then BioWaves provides a lot of services, in particular related to whale cetaceans, mitigation projects, identifying species migrations, and so on. Here's their website. You can see them with some of the SonarPoint equipment here. You might recognize some of the slides that I've used in the video series. So they are from BioWaves, our equipment here, and Tom Norris here on this page giving a presentation. He is the chief of BioWaves. So they are a good company to go with if you need these acoustic consulting services, in particular as they relate to cetaceans. All right, the final task we're going to look at is how can you make sense of a very large data set. You have many files, you know, lots of each individual file, hundreds of megabytes, sometimes gigabytes. How are you going to find what's in there? And I just want to give you some ideas as to how you can do it. In this particular example, we will look at some recordings from Monterey Bay, and we were looking here for, you know, whales and dolphins, and you end up with time domain plots in Audacity like you've seen here. Let's listen in. Okay, all this snapping you hear, those are snapping shrimp. You know, so it's a very noisy environment here. You do hear a little bit of beeping there in the background if you listen closely. That we're discussing in the currently upcoming video on hydrophone selection, so take a look at that as well. But you couldn't possibly just, you know, look through all these files and no indication that there's any whale here, and I'll go to somewhere else. Sounds all about the same. Every once in a while a boat comes by. So what to do about it? Well, one trick in Audacity is you can select a spectrum view like this. Notice how I did that. Waveform view, we had decibel waveform view, also time domain, and then spectrogram here, and it looks like this. And if you listen in on it, you kind of get to relate what sounds that you hear and that you see in the spectrogram, how they relate to each other. So all these snapping shrimps are broadband noises. So you have these vertical, very fine vertical streaks going all the way high up in the frequency range. I can adjust zoom to fit my frequency range. So now this one was sampled at 100 kilohertz. So it goes up to 50 kilohertz, and most of the energy is down there at a few kilohertz here. As you do that and you go through other files, you might identify whales. So here we are on this particular day at 0200 hours UTC in Monterey Bay. And then see what happened at 0300 hours. And notice suddenly here on the right, there are these more frequency distinct, so not as broadband events. And I'm actually going to zoom in on the time axis a little bit. So we can see it a bit closer. And here we see these curious dots. And now let's listen in on that. You hear that? Kind of faint. They're coming up on some more. Not very distinct yet. Ah, that was more distinct. I think this one has a bit more energy in it. Ah, so these are the sounds of whales. It's still quite distant, so not very distinct yet, and so on and so forth. So now we are at 3 in the morning and UTC, that is, and then at 3:20, all of a sudden, they are just the whole recording, the whole 10 minute recording, listening in. Let's see if I can make it a bit louder, if that helps. All right, we'll look at another file that I selected here. This one, we're here at 320. We'll now be going 5 minutes forward. More distinct sounds here. Very clear now and easily identified. Just enjoy that for a while. It's be coming up on 3 minutes. There'll be some more different sounds. Actually, before we go there, why don't I zoom in so we can better kind of, you know, follow it. I'm sure you can now very well relate to what you see with what you hear. Now we're coming up on some different looking sounds. Much lower frequency, hear that. And so on and so forth. So far we discussed tools from other parties like Triton for the long-term spectral averages, Ishmael for fixing positions of sound sources by signal cross-correlation. Then there's also a similar software called PAMGuard. Both PAMGuard and Ishmael also have classifiers, so you can figure out, they help you figure out what kind of species it might be. But here at Desert Star, we decided to help you a bit by concentrating on simple batch processing capabilities. You know, command line stuff, not unlike the WavMerge and SPR utility that you have learned about, where you can just point to a number of files, some sort of a processing occurs, and you get some output file that tells you what's going on. Here's an example of some experiments we did with some software that does time domain analysis, so just the strength of the signal to see if it's possible to get some useful information out of it. Here in this output from this software, we see a month worth, no, that's not correct, from April 17th through May 3rd, a couple of weeks worth of recording. And what we have is we have the file RMS signal strength, so the average signal strength in the file. And you see there's just some fluctuation here based on the file number. Those probably mostly day-night fluctuations, I believe, but not too distinct. But then the red line here, we have the maximum processing block RMS signal strength. So this software allows you to divide your file into processing blocks of, say, 1 second or some other amount of time. And we do see these very distinct peaks. So there are some files in here in this large sea of files that have short durations where there's a very strong signal. So if I go for that and let's say sort my output file here from largest to smallest, expand the selection, yes. And there we can see, okay, the file with the strongest signal is this one here at 425 at 30 hours. And I already pre-selected them in Audacity. Okay, that's what we are seeing here in the time domain. And obviously the event is this one here. It seems to be at about 45 seconds. Let me go back to my list view. Is that correct? Yeah, at time 46 seconds it says. So it found this particular event. Let's listen to it. Okay, that's quite obviously the sound of a boat going by. Let's look at the second one, but this time it's I selected the spectrogram here, and again, clearly a boat that it found. Listen to the pitch. Fairly low frequency. And then I took a section of this and did a frequency analysis. Let me do this again, just so you see how that works. Analyze. Oh, it was an analyze, I believe. Plot spectrum, here we go. And there we go. And there's the frequency analysis of this one. Then the third strongest event is this one here. Sounds quite different. You'll notice it has a much higher frequency content. Yeah, that's a different kind of out, right? Notice the general power peak here is at a few kilohertz. I'm here right now at about 3 kilohertz compared to our other identified signal, where the peak is at several hundred hertz. Now, notice how this one also has a very strong and narrow signal at about 18 kilohertz. So what would be your interpretation of that, comparing these two boats? Well, I would say this boat here, having a lower frequency power peak, is probably a bigger boat with a slower turning prop, could be a fishing boat for the area. And this 17 kilohertz, my guess is, I would have to look some closer to see if it's pulsed or not. My guess is this could very well be an echo sounder operating at 17 kilohertz. Whereas the other unit here is probably just a smaller boat, a faster turning prop. Now, of course, this helps. So now within a 10-minute file, I can see fairly quickly if there's anything of interest. You know, if I go to some other file, just sort of randomly pick any one of them. Yeah, let me go roughly the same time of day in case the animals are around at about the same time. All right. Here we go. I don't know, there's some stuff here actually. Let's see what this is. I don't think it's the same thing though, but something's visible. Is that a boat sound? Yep, that's clearly both sounds. Somebody maneuvering there maybe for fishing. So it helps the spectrogram display. But is it enough to really look at all these files this way, spending a minute or so on each individual 10-minute recording? That would still take a lot of labor. So one technique that is commonly used by the researchers are the so-called long-term spectral averages. And there's a software made by Triton. Sorry, it's called Triton. It's made by the Scripps Whale Acoustic Lab, and it's a free software, so you can download it, but it's based on MATLAB, and so you do have to have a MATLAB version running on your machine. And what Triton does is it generates these long-term spectral averages. That's one of its key features. And here we're looking at a 24-hour interval. This is from the Triton manual. And you can see here's a frequency axis. You can see distinct periods of clicking here. These are the clicks, so very broad band going up to 60 kilohertz. Here's a 50 kilohertz echo sounders. And down there, they are identifying whistles. So that is certainly a strong productivity tool. So let's look at this feature here a little bit closer to see what's going on. Again, it's 17 kilohertz here. Right now, I'm just getting frequency content up to 8 kilohertz. So I'm going to do a zoom to fit. Now we see the whole frequency range up to 50 kilohertz as it was sampled at 100 kilohertz. And I can already see that there's something going at 17 kilohertz. I'm going to zoom in on the time axis a bit here. Let me get rid of this now. Control E. And sure enough, as we zoom in the time axis, we get quite some more detail, and we can see that that stuff happening there at 17 kilohertz is pulsed. So that's clearly a depth sounder, quite clearly a boat, a larger vessel. Not smaller vessels wouldn't have 17 kilohertz depth sounders. They tend to be mostly 200 kilohertz and sometimes 50 kilohertz. So quite a bit can be figured out. So here you can see that quite a bit can actually be done with the batch processing utility. You may get to the point where you just have to look at your raw audio files for verification of what you find. This particular batch tool is not one that we have available on our website just yet. But if you want a copy of it, just send us an email and we'll send it to you. I also want to point out that, these features are fairly easily added. So if you need something specialized from us, just give us a call, send us an email. We'll give you a quotation for it. And perhaps by that way, these batch processing capabilities can become quite powerful for your use and for use of the community.